There is a specific kind of direct proof that is especially common in mathematical arguments, and it's common enough to have a special name. It's called the element method, and what we use the element method for is proving that a set A is a subset of a set B. We use the element method for proving that one set is a subset of another set, where, if you need a reminder, saying that A is a subset of B means that every element of A is an element of B. Or if I were to draw that in terms of a Venn diagram, here's the set B, and here's the set A inside B. A is completely contained in B, is another way to say this. So when we do the element method, what we want to do is we say, hey, let A and B be sets. We want to prove that A is a subset of B. How do we do it? Well, we do a direct proof of the statement for all x in the integer z or any other base set. It doesn't have to be the integer z. For all x in my base set, it holds that x in A, that statement, implies that x is also in B. So we do a direct proof of this statement for all x in my base set. X in A implies that x is in B. Now, this means that our structure of our proof is much the same as with the other direct proofs we've been doing. There is one piece about this that's I want to emphasize. It's easiest to do this when both A and B are described in set builder notation. So I'm going to give an example of a proof, but I'm going to assume that the set A is the set of all x in Z, where P of x is true. And furthermore, I'm going to assume that B is the set of all x in Z, all integers, such that Q of x is true. So this is going to make things really easy for me because this is really going to allow me to cash out my premise and my conclusion in terms of definitions, especially easily. So here's how this would go. Here's how this proof would work. I'm going to I always start the element method. Pretty much every time I start the element method, I start by thinking about the first set, the set that I want to prove is completely contained inside the other one. And I say, let x be an element of A. Let x be an element of A. That's always what I do because I'm doing a direct proof, and so I need to write my premise down. Then, next, what I do is I say, this means that. So I'm now cashing out the definition that corresponds to my premise. This means that P of x is true. Now, between here and my conclusion is going to come some steps. And then in my conclusion, so remember that what I want to do is I want to say, therefore, x is an element of B. That's where I want to land. And what I need to do is, in order to get there, I need to say, okay, whatever I do above needs to show that Q of x is true. That's the definition that corresponds to my conclusion. So my overall proof approach is much like in the case of our direct proofs we've seen so far. I say, hey, I'll state my premise, x is in A, and I'll state my conclusion farther down, x is in B. Then I'm going to cash out my premise in terms of its definition, because I'm assuming that I'm working in set builder notation, that's especially easy because the definition is just p of x, then I'm going to do some math in between and show that q of x is also true. Therefore, x is an element of B. So the element method allows us to prove that one set is a subset of another one. The method is just a specific way of setting up a direct proof, and we're going to see an example momentarily. Okay, let's go ahead and do an example of proving that one set is a subset of another set using the element method. I want to consider these two sets that I have here in green. A is the set that I've described in set generator notation for k plus 1 for k ranging through the natural numbers. And B is the set 2j plus 1 for j ranging through the natural numbers. So what are some things in A? Well, when k is 0, I am going to do 4 times 0 plus 1, which is 1. My next one is 1 times 4 plus 1, which is 5. Then I'm going to have 9, 13, and so on. And then B here, well, this is just the set of odd positive integers. So I'm going to have 1, 3, 5, 7, and so on. Now, you might notice something. I just said like 2 minutes ago, it's easier to work with the element method when you have sets in set builder notation, but I don't have sets in set builder notation. I have sets in set generator notation. And so this is why it's helpful to be able to translate between set builder and set generator notation. So I'm going to actually do a little translation now. A is the set of all x's in the natural numbers with the property that there exists a k in the natural numbers such that x equals 4k plus 1. This is a translation. I've moved from set generator notation over to set builder notation. Similarly here, B is the set of x's in the natural numbers with the property that there exists a j in the natural numbers such that x equals 2j plus 1. So now I have both of my sets represented in set builder notation. I am ready to go. So remember that what I want to do, so I want to show that for all x, this time my base set, I can use the integers, I can use the natural numbers here. It doesn't matter too much. For all x in the natural numbers, x in A is going to imply that x is also in B. So this is what I want to show, and I'm going to do it using a direct proof. So let's work outside in. I'm going to start by saying, let x in be an element of A. So I start by stating my premise at the beginning of my proof, and then I'm going to say it out here at the end. Therefore, x is an element of B. Now let's do definitions. So here, I am going to use the set builder notation in order to figure out what my definition is. I'm going to say, okay, if x is an element of A, that must mean there exists a k in the natural numbers such that x equals 4k plus 1. That's what the definition says. Similarly, down at the bottom here, where I want to get to is there exists a j in the natural numbers such that x is equal to 2 times j plus 1. So what I need to do in between is I need to take the hypothesis or the supposition that there exists such a k and use it to construct such a j. In this case, I don't actually have to do too much. I'm going to define in the middle here, let j be equal to 2 times k. Again, I've not done any math. I've just made a definition. I'm going to create a new symbol called j, and its value is going to be equal to 2 times k, where k is whatever number it was that made 4 times k plus 1 be equal to x. So once I have this definition, j equals 2 times k, I'm going to say, okay, well then I know that x is equal to 4k plus 1, and I know that that is equal to 2 times 2k plus 1, which is equal to 2j plus 1. Now, if I compare what I've shown, x equals 2j plus 1 for some natural number j, to the definition, I say, oh, I have satisfied this definition. I needed to show there existed such a j. I have done so. It's equal to 2 times the k that I picked. I am good. My conclusion follows. I satisfied the definition. Therefore, x is an element of the set B. So I have shown using the element method here that the set A that I've defined, this set, is a subset of the set B. This set, first by converting my set description into set builder notation, and then using set builder notation to cache out the definitions in my direct proof. And then just like I usually do, I work outside to in, and I fill in the math steps to make sure that I can connect the definition from my premises to the definition that leads into my conclusion.